back, right? Let me check how many of you are there. Okay, so we are good. So these were the interactive questions, all of you got. And I was asking, was that enough time or it was quick? What do you think?
My group got all through all but 2 questions.
Oh yes, last 2 questions were, I mean, you were not supposed to nail them because we didn't cover them much, but others are fine.
We
So
ran out of time.
oh, okay, that's fine. So it means a little bit, time was little tight, right? Okay, it's okay. We are learning. It's okay. We will do it for the next time. Okay, so let's go through the first question. Okay. So we did, the question is, antenna, in addition to radiating or receiving energy, it was also used to dash energy in some direction and suppress in others. So the options were dissipate, generate noise, or accentuate. What do you think, Jonathan Brado? What do you think?
Is it accentuate?
Yes. Why? What do you think?
Well, I joined the group like when we were in question 6, but we didn't go over this question. I mean,
but what do you think? What comes in your mind? Why do you think it should be third, not dissipate and generate noise?
is it because it's looking for like a negative charge?
Mm-hmm. But if you think about literal meanings, what do you think it is? So yeah, what I'm saying is, let's say you think that it is dissipate, right? So when we use an antenna, we don't want to dissipate our energy, right? We want to convert all of our input to the output, right?
So we don't want to lose power when we're trying to to the endpoint?
Yes. So that's why it could not be dissipate. It cannot be generate noise because antenna is supposed to be something that is useful, not like, it should not be like a jammer, right? So that's why it cannot be generate noise. Accentuate means that it actually, yes, you were right that due to charge acceleration, it actually accentuates the energy in certain direction, right?
Yeah.
Yeah. Thank you. I think any other comment regarding this? Okay, we are good. The next question was, antenna is a device in the transmitting mode, converts dash waves to dash waves. Lois White, what do you think?
We said that it's guided to free space.
Okay, why not others?
The reason why I think is because as it comes out of like the source and transmission line and then through the antenna, then it radiates, like it's guided and then it's out into free space, radiated into free space.
Yes, another thing that is mentioned is transmitting mode, right? So it means it transmits the energy, right?
Yes.
Okay. So, Yuri, what do you think? Is it fine? Is it right? Or do you have any other comment?
Yeah, that's what we put.
Guided to free space?
Yep.
Yeah. I think why not others? Because if you see traveling to guided, it's not true because you want to have it to the free space. If you say free space to traveling, it's also not true because the end product should be in the free space in the transmitting mode. Do you have any question about transmitting mode? What is transmitting mode?
I guess like my only question with that would be like, obviously like nothing in the antenna can really change between transmitting and receiving since it's like hardware. So what really facilitates like an antenna transmitting or receiving?
Yeah, that's a very good question. So for this question, we are just thinking about that something is transmitting the energy, right? But normally there is a little bit difference when you consider antenna as a transmitting device or consider it as a receiving device. Some of the antennas, when they are connected to the source, they act as a transmitter. And when they are connected to the matching load, they act as a receiver, because you don't need a source for the receiver. You see what I'm saying?
Right. Yeah, that makes
Because
sense.
receiver needs to accept something, not to generate something, right? Until there are exceptions. Okay? Okay. Okay, so next question is, antenna is a device in the receiving mode converts dash waves to dash waves. Krupa, what do you think?
I'm pretty sure we said free space to guided.
Okay. Why you didn't say free space to traveling?
Because in the receiving mode, it's like receiving these waves from this free space and then I guess putting them through a transmission line, which is like a waveguide. So
Yeah, that's true. Mm-hmm. Any other comment? Be good.
no, I think that was the whole thought process.
Okay, thank you. Okay, so constructive and destructive interference patterns inside transmission line connected to antennas formed by reflections from impedance mismatches between the transmission lines and the antennas are referred to as. Okay, Nick Smith, I think I saw somewhere names.
Yeah, I think in this one I didn't remember the answer myself, but in my group, I believe we discussed it to be standing wave.
Yes, but what makes us think that this should be a standing wave? Okay, I think so. The free space waves are the waves which should not be in the transmission line, right? They should be in the air. Okay. And traveling waves, I think you didn't cover, but they are the waves which travel. They just don't have the constructive and destructive patterns. So the catch here is that constructive and destructive patterns are creating the standing wave. Okay. Okay, so next is an aggregate of individual discrete radiating element in an electrical and geometrical arrangement is referred to as an. Cedric, Noel.
Yeah, for that one, we said array.
Okay. Why you think this could be an array?
Because I mean, a continuous source is not really like multiple antennas, and I feel like if you have more than one antenna, like a lot of antennas, that would just be called an array.
Yes, that's right. That's very much right. I mean, except an array, there is no option that says multiple radiating elements, right? That's why it should be an array. Okay, so the next question is, to create radiation, there must be a Bryce.
For the first one, we said that was a time varying current. That's one of the factors that can create radiation.
Yeah. And we were talking about charge, accelerating charge, but we were not talking about accelerating current, right? So that's right. That's time varying current. Okay. And Shane, what do you think about 7?
So for this, we decided it should be accelerating charge because that is effectively a time varying current when the charge is accelerating or decelerating potentially.
Yes, that's right. Any other comment? you have or someone else have regarding these? Okay, if you're good. So the next question was, radiation can be created by, so we can tackle 9 and 10 simultaneously. So what is radiation can be created by the smooth wire, discontinuous wire, infinite length wires, bent wires. What do you think, Christopher?
We had discontinuous wires for number 9, and then for number 10, bent wires.
Yes, because we said that there should be some discontinuity, right? There should be some disruption for time varying current,
Yeah.
right?
Yeah, correct.
Okay, that's right. Okay, sounds good. I think it. Okay, so now if you say the distance between two half-period free space wave and the last question. I didn't expect you to do this because I want to talk about it a little bit more because we have not covered it in detail in the first chapter. So it's okay, okay? So, so last time I actually, from the feedback, I actually got to know what I was mentioning before, that there are two topics that were bothering some of you were equivalent circuit and spherical coordinates. So equivalent circuit, we will cover in detail later. That's why I just did this little bit of introduction, but spherical coordinates we need to understand, okay? So I will just go through a little bit of equivalent circuit first, because that's what I think. Let's make ourselves comfortable about it. We will just do a little bit of introduction, and then we will move to spherical coordinates. Some of you also have very, very good comment that they said that it's hard to go through the slides with this intense course. So that's right. We will use what you should say, the board to write things whenever it's possible. So it's not all PowerPoint slides, okay? So I really appreciate you guys give me feedback, because it will help me to, you know, get it better. So let me, now I forgot how I was doing that before, 1 minute. So if I have to broadcast what I was doing before. I literally forgot. I'm using this iPad after a long time, and I forgot how to broadcast my notepad. That's strange. Okay, let me do it here. Maybe we will do it at the end, transmission line first. I will do the lecture, okay. So lecture 3. So I just thought that I didn't cover this wavelength before. So let's do it for now, and then we will move. So wavelength, we think, is the spatial period of periodic wave, the distance over which the wave's shape repeats, okay? So if you see here, this is the wave. I feel my echo, 1 minute. If you see here, there is an wave here, and you can see that there is the period that it is completing, and we say that the crest to crest is 1 lambda, and trough to trough is 1 lambda, right? So if you see here, this is a sine wave, and that will be the 1 wavelength. I think you know this before, but just repetition. So the question in interactive questions was, the distance between two half-period free space wave is. What do you think it would be? Looking at this figure. I know you know the answer, maybe you checked it, but just in case. Eric?
Is it lambda over 2?
But why do you think it is?
Because I got it wrong the first time and just want to check the answer.
Yes, that's right. Okay, I think the reason is, if you see here, so what is half period wave? So if can you see my, so this is the 1 period, right? This is complete 1 period, right? And from here, the next wave is starting. So this is half period, and just forget about this, and this is half period, right? So if you see the distance between them, the half periods is lambda by 2, right? Do you understand what I'm saying? Or if you just say that this is the wave, and this half period and this half period distance is lambda by 2. Right? Michael, do you have a question about this?
No, so
You
it's
good?
basically just the distance between where it crosses the x-axis.
Yes. Yeah, I think so. It's not that distance between two complete waves. It's just the distance between two half period waves. It could be like this distance, right? Okay. So another thing I think it's worth discussing is what a standing wave looks like. So when we say that it is combination of destructive and constructive patterns, it's like that when your waves are traveling like this, and when they are coming back, they make the constructive and destructive patterns. And another thing is that they try to remain at the same point. They just don't change their position. That's make them a standing wave. Okay. And then another thing which I think is very important to discuss is the frequency and wavelength relationship. So when we say that frequency is inversely proportional to the lambda, it means that we are saying that longer the wavelength, lower the frequency. Shorter the wavelength, higher the frequency. Do we understand this? Right? So here you can say that wavelength is shorter, but frequency is higher. Similarly, you can see here that wavelength is longer, but frequency is lower. Right? Okay, so I think that's an important thing to do. Okay. Now again to the spherical coordinates. So we said last time that this would be the coordinates that we are using. But in some book, if you refer, there can be the phi, and this could be the, what you should say, theta. But I think that the problem is that how we are interpreting it in terms of what you should say, rectangular coordinates, right? So 1 minute. Can you? No, you cannot. Okay, I just do it here. So can you see that? Yes, okay. So if you see here, what I'm trying to say is that this is pen, and this is the R, right? And this is another, what you should say, a thing that looks like an R. But what we were saying here was that if you have this thing, that is your R making theta, and this is your Z, and this is your Y. So this R is making right angle triangle here, and this is its may be base, and this is its perpendicular, right? We are good about this. I'm just drawing this stuff here. Okay. So we know that we can say base is actually R cos theta, right? And perpendicular is actually R sine theta, right? So this is our R sine theta, and this is our R cos theta. Are we good about this? Right? So if we say that we are just taking an image of this right angle triangle here, it will be something like this, right? So this theta is projected here as a theta, right? Are we good about this? Any questions? Okay, so if it is projected like that, this R cos theta will be here R cos theta. And if I just move this one little bit. And this projection here will be R sine theta, right? Do we have question about this, or we are good? You can ask why you said that this is R sine theta, right? Because if you see this triangle, it has this angle and it also has this thing, right? It should be coming from like the origin. But now if you see here that this is Y and this could be another axis X, and if you forget about the above triangle, you can say that we can project this as this thing, right? And if you forget that this is your sine theta, you can just say that this is your rho, and the angle it is making with the x-axis makes it another triangle, which is, so the base normally in the triangle is which is connected to the angle, right? Which we are considering. So this is the base, which makes it, let's say we say R sine theta is rho. So it will make this rho cos phi, and this will be rho, sorry, not this. This will be rho sine phi, which we can replace with the r sine theta, right? Or it's just lost here. 1 minute. I should do it maybe again. Okay, so what I'm trying to say here is that this is my r, this is my theta, this is my r cos theta, this is my r sine theta. Its projection is here. If this is the angle, this will be rho, and this will be x, and this will be y, and this will be c. So now if you see here, this will be another triangle, which is making phi. And this is rho. What should be this one? The rho what? Is it sine or is it cos?
Sorry, for which area?
Sine.
This one, rho, what should I write here?
Would it be sine?
Yes, why?
I'm just kind of imagining like from the top triangle, like the projection down.
Yes, it is sine because it's the opposite of phi angle, right?
Right.
So what I'm trying to say is if this is your right angle or triangle, and this is your angle, the opposite of these two sides will be sine because it's the perpendicular, right? So your sine will be always this one. Right? So if you see only this triangle, this one here, right? So in this triangle, or you can just say, this triangle, this is opposite of phi will be rho sine phi, and adjacent to phi will be rho cos phi, right? So similarly, that is happening here. So adjacent to phi, this is rho cos phi, and opposite of phi, this is rho sine phi. You got it, Fabian?
Yeah.
Okay. So now you understand that this is rho cos phi and this is rho sine phi. But we need to figure what rho is, which is the projection of this arm. That's why you say that it is rho is actually r sine theta, and you are just replacing the things. So basically x was rho cos phi and y was rho sine phi, and you just replace it with r sine theta and it becomes r sine theta cos phi, r sine theta sine phi. Okay, are we on the same page? Jack, what do you think?
Yes, I'm getting you.
Okay, I mean, if you have any questions, you can ask me now because it's really important for antennas that you know spherical coordinates, okay? So if it is something is not clear, just ask me, it's okay. Aaron, do you think it's fine?
I think so, yeah.
Do you have any confusion?
Not right now. I might like during like an example kind of problem, like with like using actual like values and stuff. But like from the picture, how you explained it, it makes sense.
Okay, so for the picture, it's fine. Right?
Yeah.
Okay, so that's good, but I think I have to erase this to move on. Okay. Okay, so still there are. So we were discussing this before, right? Now I want to check what I was asking you before, that maybe if I go here, can you see this screen? Like, can you see this? Okay, so if you see, I just want you to visualize this thing, okay? So the problem here is they just, what you should say, swap the angles that I was telling you. They are considering this as phi and this is theta. It just doesn't matter. So if your r is small, it will go to the point, right? So if you increase your r, both things are increasing.
Professor?
Yes.
I only see a blank slideshow
Yes,
screen
that's what
with
I
just
was
the
asking.
link.
1 minute.
Yeah. Okay.
Can you see that now?
Yes.
Yes.
Okay, so what I was saying, if I'm making it 0, this is like this, right? So there are 3 coordinates, rho, theta, and phi. The problem is that they are considering this as phi and this is theta. I'm just giving you the physical interpretation of this. So if you increase rho, it's like that, right? Your whole r is increasing. So this is phi for us, okay? Just don't consider it as theta. This is phi for us. So phi is like this, right? You understand what I'm saying, doing? So this is total, like this is maybe 360 phi, okay? And this is theta, which for us. So it means that this is your theta, okay? Okay, but another, this is theta for us. So that's what I was asking you in the last lecture, that if your theta is 90, what will happen? So this is your theta is 0, right? So when you increase your theta, this is your theta 90, right? It becomes a disk because everything, like this theta here is 90 here now, right? So it will become a disk, okay? And if you increase your theta more, it will be on the opposite side of this. Am I clear about this? Is it confusing? Is it good? Okay, so let's do it, try to do this here. This is our phi. So phi means that this is your phi is 0. And when I'm seeing phi, all the other things are changing. Like R can change, theta can change and stuff like that. So when you are moving it, you are actually trying to say that this all plane is considered as phi, right? Your phi is at certain angle, but your theta and R can be changing. So we got it, this one. So what do you think right now? What is the angle of phi here?
Is it
Ria,
90 degrees?
what do you think is the angle of phi here? Okay, who's?
Shane said 90, and I agree with 90.
Yes, this is 90. That's right. That's very good. So what is the angle of phi here? Saad, what do you think?
I'm not sure.
Okay. What do you think? Sorry about this.
Is it 180?
Yes. It's 180. Sorry. Saad, what do you think this angle is?
Is it 0?
Yes. And when you move here, this is how much difference than 0? Is it a right angle?
Wait, can you repeat your question?
So what I'm asking is, when this was 0, right? And what is the angle between X and Y here?
90.
90. So this is at, phi is at 90 right now, right? Oh, sorry, that was not 180. Okay, so this was 90, okay? Got it? Saad?
Yeah.
Okay, now if we move here. Andrew, what do you think this angle is?
That's 180.
That's 180, yes. Sorry about that. I thought about that this was 0. So that's 180, right? And this angle?
270.
270, and then back to 0 or 360. So are we clear about this? Right? So that's how your phi is changing, right? Okay. So this one is the easiest one, in which you have no R or maximum R. So it means that your phi and theta is changing, but your your phi and theta are constant, but your R is changing, right? So are we good about this? Spherical coordinate, imagination? Or do we have any questions? Do we have questions about this theta thing? This is very interesting, I feel. So we good to go? We good to move on? Okay.
Oh, Doctor, can I actually have one quick question?
Yes, go ahead.
When it's like the bottom, like the top cone, it's up to 90 degrees, but then when it's higher than 90 degrees, that's when it shifts to like the bottom cone.
1 minute. So, okay. So consider this is your theta, okay? So your theta is 0, you cannot see anything, right? So what do you think this angle would be of theta? Everything else is changing, just your theta is constant. What do you think this angle should be? This should be greater than 90 or less than 90?
Should it be less than 90?
Yes. Why? Why you think it's less than 90?
Well, I just know like when it's a disc, that's when it's 90 degrees. So since the radius still isn't growing to like that rate, it's still less.
Okay, one more thing I think, make here is so, yes. So if you see here in this scenario, this is the angle, theta, right? Right? Yeah. And when it's 90, it's here. Your thing is here, right?
Mm-hmm.
So that's why you are saying this is less than 90, right?
Okay.
When this will move here, this will come here. This is the 2D scenario. This is greater than 90.
Yeah.
Right?
Mm-hmm.
So if you here, this is 90. And if you are here, this is greater than 90.
Yeah, okay.
Sounds good?
Yeah, that makes sense.
And this is 180. Right?
Yeah.
So we're good about this? Okay, sounds good. I am spending so much time on this one because I feel that's the basis of antenna theory. If you don't understand 3D coordinates, you will not understand radiation patterns. Okay, so that's why I want to make sure that every one of us knows what we are doing. Okay. Okay, so we are good till here. So leave this one. We will do questions again. Okay, and there was one more suggestion is that some of the slides we pass quickly because we will cover them later. And they were just for the introduction. Okay, so now radiation pattern. So what is radiation pattern? In antennas, radiation pattern is the mathematical or graphical representation of the radiation properties. Okay, what are the radiation properties? Amplitude, phase, and polarization. Okay, so if you see here, we will discuss that, what is amplitude, what is phase, and what is polarization. But here you can see that we all the time describe them as the function of theta or function of phi, which is the spherical coordinates. So we now know that this is phi and this is theta and this is our changing r. Now we will describe what this radiation pattern is right now, but that's how antenna's radiation pattern looks like, that you will see a major lobe, you say that, and then some of them are minor lobes as well. So we will come back to these theta things. These are called steradians. We will come back to them. But right now I'm just introducing that this is your radiation pattern looks like. Okay, sounds good? Okay, so when we are talking about amplitude patterns, there are two types of amplitude patterns. One is field pattern and one is power patterns. So field pattern is where you show field plot, like E plot or magnetic field plot in linear scale. And power pattern is when you show a square of these plots in decibel scales, right? So normally I feel comfortable when I deal in the decibel scales in terms of antenna, but there are plots which are in the linear scale and decibel scale both, okay? So this is an example of the field plot and the radiation plot, or the, yes, power pattern, in which you are describing an antenna's behavior. So if you see this thing, you are seeing different colors. Different colors means that they have different intensities. So if you see this is red, this has the higher intensity, blue has the lower intensity, and light blue is like the, different strength levels. What they are saying that these patterns are showing, this is an array of 10 elements, and array of 10 elements with lambda by 4 spacing, which means maybe or maybe not. It can be a linear array, it can be a 2D array. So when you say 2D array, it means that you have 5 by 5 elements, like something like this. 1, 2, 3, 4, 3, 4, 5, 1, 2, no, 10 elements, sorry. It should not be like this. It's be 5 by 2 elements. So these are 5 by 2 elements. 5 by 2, like you have 2 rows and 5 elements in each row, and these are all transmitting at the same time, creating an array. And this 10 element array has the spacing, each element has the spacing of lambda by 4 between each other. Okay, sorry, if they are saying linear array, so linear array means it's not 2D array. So linear array means that it's something like this. 2, 3, 4, 5, 6, 7, 8, 9. So this is your linear array in which you have all the elements in line, and the distance between each element is lambda by 4. Okay? Sounds good? So this is the power pattern of the field pattern of the linear array. Okay? What is half power beamwidth? Half power beamwidth is when all 3 patterns yield the same angular separation between the 2 half power points. Means that you can also, in other terms, you can say when your antenna is radiating half of its power, right? This is the maximum power, and this is the half power point. Okay? So half power point, it's when it radiates 1 by 2 of its power, right? 1 by 2 of its power in terms of field means 1 by square root of 2 of the field, okay? Am I clear about this? So 1 by square root of 2 is 0.707, right? So it's half power or 1 by square root of 2 point where your antenna is radiating the half power, okay? So at this point, when you measure the, what you should say, spread of the main beam, that's your half power beam width, okay? So means that how much angle is between these 2 points, that's your half power beam width. Okay? You feel sleepy?
I have a question about that.
Yeah.
It's more of just like a practical question. So
yes.
Is like, so half power beam width, I'm guessing that's like used mainly because like if it's less than half power, like there wouldn't really be any practical use for like the signal. Is that kind of where that comes from? Or like why is half power beam width important?
Yes, that's the main point, that we want to know where till when the antenna is radiating its half power. Beyond that, we say that it may not be much of our use. Okay, so if we say that antenna's half power beam width is 38 degrees, that means that antenna is covering the range of 38 degrees. Okay, some antennas have more of the beam width, like the 50-degree beam width, means they are covering the 50-degree region. Okay, some antennas are covering 2-degree beam width, means they are covering a small region. So more arrays cover small region. They are more of the directive. And normally one antenna element covers larger beam width. So if I just draw this thing again, So if you have something like this, then your half power beam width will be small, right? Maybe it's 5 degrees, right? If you have something like this, your half power beam width will be large, maybe 50 degrees, right?
Right, yeah, that makes sense.
So we are clear about this? Okay. So linear scale, if you see here, yeah. So if you see here, the difference between the field pattern and the power pattern is exactly what I was telling, that this is the half point and this is 0.707 point. And this power is the square of the field. That's why you are seeing something like this, okay? Okay, now if you see here, that's when you are seeing the dB plot. So in dB, your half power point is displayed as -3 dB, okay? Because when you take the log of this, I think it's 10 log of this, so it should be -3 dB, okay? Ten log of 0.5. And when normally, you know, when you do the dB plot, it actually enhance the change, right? So similarly here, you are seeing the more bigger side lobes are, what are side lobes? We will cover that later, but that's how you are seeing it. So are we clear about half power beam width? Sarah, are we clear about this?
I think it makes sense.
Okay. Okay, thank you. Let me. Move forward, okay? So we will now describe some of the terms that we have seen below, like before. So what is major lobe? So major lobe is defined as the radiation lobe containing the direction of maximum radiation. So this is your major lobe, right? And similarly, this is your major lobe. Okay? So where your maximum direction is going, or maximum radiation is going. What is minor lobe? Minor lobe is any lobe except a major lobe. So it could be any lobe. If there is, most of the antennas have major lobes. Some of the antennas have 2 major lobes, but other than the major lobe, any other lobe that you're seeing is minor lobe. So what is lobe? Lobe is kind of this pattern that we have with an antenna. So these are all lobes, the small, big, whatever, it's all lobes, okay? So if we move forward, a side lobe, what is a side lobe? Side lobe is a radiation lobe in any direction other than intended lobe, okay? Usually a side lobe is adjacent to the main lobe and occupies the hemisphere in the direction of the main. So your question can be, why they can not all be a side lobe? What do you think? how many of them are side lobe and how many of them are not side lobes. So the side lobes are actually the lobes which are adjacent to the main lobe, but they are very, very small. Okay.
So what would be the difference between the side lobe and a minor lobe, since like anything that's not a major lobe is considered to be a minor lobe?
Yes. So if you see here, there is a side lobe and there is a back lobe, right? So the back lobe is something that is being transmitted on the opposite side. Like this one is the back lobe, right? But all the others will be the side lobes. So I think what we are doing is the differentiation between back lobe and the side lobes. So back lobe is also a minor lobe, side lobe is also a minor lobe, but back lobe is the lobe that is transmitting at the opposite side. Okay. So these are all side lobes, but these are all minor lobes, but these are side lobes, and this is the back lobe. Sounds good? Another thing is that this is 3D, not a 3D plot, 2D plot, but this is when we are opening it up. So this is the polar pattern, and this is the linear scale. So if you see in the linear scale, it's describing you the angles like this. So this is your 0 degrees. So this is adjacent to this one. Okay. And this is the 180 degree. That is the back lobe. That is adjacent to this one. Are we clear about this? Is it too boring? Very.
One thing I noticed is that, so like the beam width on like the back lobe is like, I guess the second largest compared to like the major lobe. Is there like maybe any explanation for that, or like how the beam widths of like the minor lobes change and why?
So it depends on the design of your antenna. Sometimes back lobes have larger beam width, but it is not that a generalized thing.
Okay, so that's not always, that depends on like
Yeah.
the shape and
Yes.
type. Okay.
It's just dependent on the application. But major lobe, if your antenna design is right, major lobe should have the largest beam width and should have the maximum intensity. Only then it's called a major lobe. Okay,
yeah, that's helpful. Thank you.
Another thing you can see here is the first null beam width. That is another thing that you're seeing here. Okay, so first null beam width is, I didn't write it here, but I think first null beam width is, so this is your null where you are seeing the 0 thing. So if this is your lobe, and this is your side lobe, this is your null, where you are seeing a 0 intensity. Okay, so this is a null. So the angle between your two nulls is the first null beam width. So why it's called first null beam width? Because you have more nulls here. So this is another null, right? But you just consider the beam width of the first null. Are we clear about this? Anything you see and doesn't make sense? I think there is another thing that should make sense is the plus and minus signs. We will talk about them later. Okay. Anything else? Okay, let's move forward. So this is the 3D pattern. Previously, we were seeing the 2D patterns, but this is a 3D pattern. And one more thing, if you see here, we just described it in terms of spherical coordinates. So this is your theta, and this is your phi, right? And normally you see that we are saying our major lobe is where the theta is equals to 0. That makes sense, right? Okay, so now we are saying minor lobe usually represent radiation in undesired direction, and that should be minimized. So what we are trying to say is when we design an antenna, we want that minor lobe should have very, very less energy in it, and major lobe have a large energy in it. It means if the major lobe has a large energy in it, it means that our design is optimized because we are doing what we are intended to do. So side lobes are normally the largest of the minor lobes. So these are the side lobes. These are the largest among. Normally the adjacent side lobes are larger, but it is not necessary. Okay. And the level of minor lobe is usually expressed as the ratio of the power density in the lobe in question to that of the major lobe. Means that if this is your 1, so this will be the ratio between the side lobes and your, what you should say, major lobe. So that's what you are saying. So you are normalizing it with respect to the major lobe. Okay. So if I am saying that my side lobe is minus 20 dBs, it means I am describing it with respect to my major lobe, right? So we are saying that this is minus 20 dB, means that it should be 0.25, 10 log 0.15 dB. Will make it 0.2 minus 20. Okay. But we will also look at its formula. It's just the description we are, like the introduction we are doing.
Can I ask a quick question?
Yes.
The last bullet says side lobes levels of negative 20 dB or smaller are usually not desirable in most applications, but wouldn't a smaller side lobe be more desirable?
Yes. Okay. So yeah, that's a good question. So normally what happens is that we want to have a minimum side lobe, right? So it means that we want to have a minus 40 dB side lobe, right? But we do not want to have a side lobe that is greater than what you should say, minus 20 dB. So I think here it should be, I mean, when you add a minus, it's become flip thing, right? So it should be side lobe levels of minus 20 dB or smaller are usually not desirable. I think it just means that we want to have a smaller side lobe level, or we do not want to have side lobes at all. Okay.
So like, would this be right to say that like negative 40 dB is like a stronger signal than negative 20 dB? So that's why like the negative 20 dB is like smaller?
No.
Or that's not true? Okay.
Right. So, okay. So normally in antennas, we have power in positive dBs, right? So like you may have heard 10 dB gain, right? Or 9 dB gain or 20 dB gain. Some antennas have 60 dB gain. So we are talking about their major lobes gain or major lobes intensity. When we say that side lobe level has minus 40 dBs, minus 20 dBs, or minus 60 dBs, it means that this is the lobe which is not supposed to radiate, but is radiating a very, very minute level. So if your side lobe has minus 10 dB, it's a bad antenna because minus 10 dB is quite a bit of a power to, radiate. Does this make sense? So side lobe level should never go into positive, right? And it will be always negative because it's a ratio of the level between major lobe. So what I'm trying to say that if you have a larger side lobe level, something like here, it will be greater. It will not be minus 20, it will be minus 10 or minus 5, right? If it is smaller, it will be more, like it will be minus 60 or something like that. Okay? Yes. Okay. So, yes, so I think this explains better. So attainment of side lobe level, let me check the time. Okay. Attainment of side lobe level smaller than minus 30 dB usually requires very careful design and construction. Low side lobe level ratios are very important to minimize false target indication through the side lobes. Does this make sense? Like what I'm saying is that if you have side lobe level, you can, if it is using as a radar, you can do a false target detection because you are sending energy in non-intended direction, right? Or unwanted direction. So that's why you do not want to have a side lobes. That's what we are trying to say. Sounds good? So we are stopping it here, and there is a minute paper 3. Please fill it out. And I think from now on, when we have covered the spherical coordinates, we will be moving towards some of the problems and stuff like that. But I think we made a strong base to start for antennas, okay? So even now, if you have some problems regarding, spherical coordinates, please come back to me because I really want you guys to understand that to move forward, okay? Sounds good? Thank you for today. And sorry for the boring lecture if it is. Okay, thank you, bye.
Thank you.
Thank
Have a
you.
good day.
Have a nice day.
Have a nice day.
Bye.
Good day.
Thank you. Bye.
Bye.